Hello everyone, in this video I'll be talking about how to interpret IR spectra, and previously what I have covered about IR spectroscopy is available on my YouTube channel. There are a couple of videos which I will discuss. First, the introduction of IR spectroscopy, and then what is the instrumentation of IR spectroscopy, and then I have discussed the sample preparation for IR spectroscopy. Now we are going into more of a applying part, like what information we can get from IR spectroscopy and how to interpret the IR spectra. So what to look for look for when examining infrared spectra, that is the key question. So if you let me pick the highlighter. So an infrared spectrometer determines the positions and relative sizes of all absorptions or peaks in the infrared region and plots of them as a piece of paper. This plot of absorption intensity versus wave number sometimes is referred to as the infrared spectrum. So the figure 2.4, as you know that I'm following the Pavia book, Introduction of Spectroscopy. So if you have already that book, and you can open that book, and I'm explaining the points from that book. So figure shows typical IR spectrum of 3-methyl 2-butanone. The spectrum exhibits at least two strongly absorbing peaks at 3000 and 1750% for CH. This one is for CH, and this one is for the Carbonyl Group, stretching frequencies respectively. The strong absorption at 1715, that corresponds to the Carbonyl Group, is quite intense. In addition to the characteristic position of the absorption, the shape and intensity of this peak are also unique to the Carbonyl Group, carbonyl bond. This is true for almost every type of absorption peak. Both shape and intensity characteristics can be described, and these characteristics often enable the chemist to distinguish the peak in potentially confusing situations. For instance, to some extent, Carbonyl Group and carbon double bond carbon are absorbed in the same region to the infrared spectrum. So carbonyl absorbed at 1850 to 1630, and carbon double bond carbon absorbed from 1680 to 1620. So as you can see, there's a kind of an overlap between carbonyl, and slight overlap, I would say, between carbonyl and the double bond carbon double bond carbon. However, the carbonyl bond, this one, carbon double bond oxygen, is a strong absorber, whereas the carbon double bond generally absorbs only weakly. So the difference between this, we can say it's intense, and this is less intense. Hence, trained observers would not interpret a strong peak at 1670 to be a double bond, or a weak absorption at this frequency to be a carbonyl group. So from the intensity of the peak, you can determine whether it's a, so for example, if you see a peak at 1680, now you can think of two things. It could either be carbonyl group, or it could either be the carbon double bond carbon. Now, if the intensity is too high, it's very intense, then it's going to be the carbonyl group. If the intensity is low, then it's going to be the carbon double bond carbon. Okay. The shape and fine structure of a peak often gives clues to its identity as well. Thus, although the NH and OH groups, OH regions overlap. So as you can see this in this box, for OH we have the region 1360-50 to 3200, and for NH it's 3500 to 3300. So these two regions quite overlap, so it's really hard to pick which is for OH and which is for NH. But from the shape and fine structure of peak, we can determine which peak is for which. Okay, this is the spectrum of 3-methyl 2-butanone. And this is the sp3ch, that's the CH peak, this one. And this carbonyl group is this one. As you can see, it's very intense at around 1715. and the rest of the signals, this is a bending region or fingerprint region, and this is the functional group region. From 1500 to 4000 is called FG region or functional group region, FG functional, and this is from 1500 to 400, it's called fingerprint region, FP region. So FP for fingerprint and FG for functional group region. So you must assign the characteristic peak of any given molecule from the given IR spectra. For example, this was the spectrum that was given to you for this molecule 2-methyl-2-butanone, and as you can see, this molecule contains the ketone group, which is this one. So you must assign the peak for this carbonyl, and you must assign the peak for CH in the functional group region at least. If you cannot assign these fingerprint peaks, that's okay, but you must assign the functional group region peaks. Now if you look at the comparison between the carbonyl group and double bond absorption peaks, sometimes both appear at the similar region. So you can see this is a tiny peak which is less intense, less intense, and this is a quite intense peak for this carbonyl group, and the region for these two peaks is not it's almost same, but from the intensity we can identify that which peak is for carbonyl and which peak is for carbon double bond carbon. So the point that I was making earlier, that if the peak is intense, that will correspond to carbonyl group. If the peak is small, less intense, that will correspond to carbon double bond carbon. Similarly, there were ambiguity about OH and NH2 group. So which peak belongs to OH and which peak belongs to NH, as they both appear in the same region. As you can see from the shape and fine structure of the peak, this is for OH and this one is for NH. You can see the V-shaped structure is for the OH, and this shoulder thing, couple of peaks for NH2. So this is how you can predict from the shape of the peak that whether or not this is OH peak or NH2 peak. So primary amines gives 2 bands, secondary amines give 1 band, but the peak shape is really important in this case, as OH is a very broad, gives you a very broad V-shaped type peak, where NH2 gives 2 band, gives rise to 2 bands. And this is a typical IR spectrum. So wave number at the x-axis and percentage transmittance on the y-axis. That's the transmittance on the y-axis, and that's the wave number on the x-axis. The NH absorption usually has 1 or 2 sharp absorption bands of lower intensity, whereas OH, when it is in the NH region, usually gives a broad absorption peak. That's the difference. So the NH gives the short peak, whereas OH gives the broad peak. Also, primary amines give 2 absorption in this region, whereas alcohol as pure liquids give only 1. That is also the difference between NH and OH peaks. Figure 2.6 also shows typical pattern for CH stretching frequencies at about 3000 per centimeter. Therefore, while you study the sample spectra in the pages that follow, take notice of shapes and intensities. So these two are important in IR. The shape and intensity of the peak. They are as important as the frequency at which absorption occurs, and the eye must be trained to recognize these features. Often when reading the literature of organic chemistry, you will find absorption referred to as strong, small s, medium, small m, weak, w, broad or sharp. The author is trying to convey some idea of what the peak looks like without actually drawing the spectrum. Now, next important topic is correlation charts and tables. To extract structural information from infrared spectra, you must be familiar with frequencies at which various functional groups absorb. So you should know that OH group absorbs at this region, carbonyl group absorbs at this region, benzene absorbs at this region, aldehyde absorbs at this region, ketone absorbs at this region. So you must have an idea that which functional groups absorb at which position. Or in other case, you may consult infrared correlation tables, which provide as much information as is known about where the various functional groups absorb. The references listed at the end of this chapter contain extensive series of correlation tables. Sometimes the absorption information is presented in the form of a chart called correlation chart. Table 2.3 is a simplified correlation table. A more detailed chart appears in Appendix 1. The volume of data in table 2.3 looks, this is the table 2.3, okay, we are coming there, looks as though it may be difficult to assimilate. It's difficult to digest. However, it is really quite easy if you start simply and then slowly increase your familiarity with an ability to interpret the finer details of the IR spectrum. You can do this most easily by first establishing the broad visual pattern of figure 2.2. That is the figure 2.2. That is the figure 2.2. Okay, so figure 2.2 quite firmly in mind. Then as a second step, memorize a typical absorption value, a single number that can be used as a pivotal value for each of these functional groups in this pattern. For example, start with a simple aliphatic ketone as a model for all typical carbonyl compounds. The typical aliphatic ketone has a carbonyl absorption of about 1715 plus or minus 10 per centimeter. That is the region for aliphatic ketone. Either it could be 1725 or it could be 1705. So either plus minus 10 wave number is required in this one. Without worrying about the variation, memorize 1715 as the base value for carbonyl absorption. Then more slowly familiarize yourself with the extent of the carbonyl range and the visual pattern showing where the different kinds of carbonyl group appear throughout this region. See for instance section 2.14 page 52, which gives typical values for the various types of carbonyl group. Also learn how factors such as ring strain, conjugation affects the base values, in which direction the values are shifted. Learn the trends. Always keep the memorized base value 1715. It could either go up, it could either go down depending upon several factors such as hydrogen bonding, resonance, conjugation, ring strain. As a beginning, it might prove useful to memorize the base values for this approach given in table 2.4. Notice that there are only 8 of them. This is the table 2.3. Simplified correlation is described here in this one. And from this table you can see the type of vibration: stretch, bend, bend, stretch, out of plane bending, stretch, out of plane bending, stretch. This is the CH, and it could either be present in alkanes, aromatics, alkynes, and the aldehydes. So the CH bond is present in alkanes, alkenes, aromatics, alkynes, and aldehydes. So if CH unit is part of alkanes and you observe a stretching vibration, it should appear at 3000 to 2850 per centimeter, and the intensity should be S. What is S? We just discussed. Strong. M is medium, W is weak. If you see a peak, the methyl group bending gives you a peak at around 1450 to 1375. The intensity of the peak is medium. The CH2 unit bending gives you a peak at 1465. Intensity is medium. Alkenes gives you the stretching peak at around CH 1300 to 3000, and the intensity is medium. CH3 of alkenes gives you the peak at around 1000 to 650, and the intensity is strong. CH2 of alkenes gives you the peak at around 1000 to 650. Aromatic stretch CH gives you peak at around 3150 to 3050. Out of plane bending for aromatics appear for CH 900 to 690, and the peak intensity is strong. For alkynes it appears 3300 and the peak intensity is strong. And for aldehydes it appears at around 2800 to 2700, and the peak intensity is weak. And this is for CC single bond of alkane, not interpretively useful. C double bond C of alkene gives you a peak at around 1680 to 1600. The intensity might be medium or weak. The carbon double bond carbon of aromatic gives you peaks at around 1600 to 1475. Intensity might be medium or weak. Carbon triple bond carbon of alkynes gives you peak at around 2250 to 2100. The intensity might be medium or weak. The carbonyl group of aldehyde gives you peak at 1740 to 1720, and the peak intensity is strong. The ketone group gives you peak 1725 to 1705. The peak intensity is strong. Carboxylic acids gives you peak from 1725 to 1700. Peak intensity is strong. Ester gives you peak around 1750 to 1730. Peak intensity is strong. Amide gives you peak at around 1680 to 1630. The peak is strong. Intensity is strong. Intensity of peak is strong. Anhydride gives you two peaks, one at 1810 and another at 1760, and the peak intensity is strong. Acid chloride gives you peak at 1800, and the CO of alcohols, ethers, esters, carboxylic acids, anhydrides, phenols gives you the peak at around 1300 to 1000, and the peak shape or intensity is strong. Now next important is OH, which is present in alcohols, phenols, free or H bonded. So in alcohols it gives you at 1365, 3650 to 3600, and the peak intensity is medium if it is free. If it is hydrogen bonded, then the frequency is lowered and the peak appears at around 3400 to 3200, and the peak intensity is medium. And for the carboxylic acids, the peak for the OH group appears at around 3400 to 2400. It's very broad peak and the intensity is medium. And for the primary NH, primary and secondary amine and amides, the stretching occurs at around 3500 to 3100, and the peak intensity is medium. And the bending occurs at around 1640 to 1550, peak intensity might be medium to strong, and Cn for amines gives you peak at around 1350 to 1000. C double bond N for amines and oximes gives you peak at around 1690 to 1640. C triple bond N nitriles gives you peak at around 2260 to 2240. XCY allenes, ketenes, isocyanates, isothiocyanates gives you peak from 2270 to 1940. Nitrogen double bond oxygen nitro group gives you peak at around 1550 to 1350. Mercaptans SH groups gives you peak at around 2550. Sulfoxides gives you peak at around 1050. Sulfones, sulfonyl chlorides, sulfates, sulfonamides gives you peak in this region from 1375 to 1300 and 1350 to 1140. CX halogens fluorides gives you peak at 1400 to 1000. Chloride 1785 to 540. Bromide and iodide less than 677, and the peak intensities are strong. This is the table 2.4 base values for absorption of bonds. So the base value for OH is 3400, plus or minus could be happening because of number of factors. NH gives you peak at 3400. CH gives you at 33,000. C double bond 2250. Triple bond at 2150. Carbonyl 1715. Double bond 1650. Single bond between carbon and oxygen at 1100. Now I would like to end that talk here, and in the next topic I will be discussing how to approach the analysis of a spectrum with, or what you can tell at a glance. So these are the useful tables and correlation charts, characteristic peaks that you can remember, and then from that on you can go on to interpret the IR spectra and assign the peaks and do the assignments in the IR spectroscopy. So keep watching this channel. I'll be uploading more videos about IR spectroscopy from the Pavia book, and thank you for watching. Take care. Bye.